yesterday you heated up a piece of metal and did some measurements of mass and before and after temperatures. You began by heating up a piece of metal in a hot water bath to approximately about 100 degrees Celsius. If you please take a look at your results table, and if you check your metal sample column for initial temperature, your initial temperature should be in the 90s or close to 100. Hopefully you remember to take the mass of your metal sample. Okay, lots of nods, good. Then you took out the piece of metal and you put it into a coffee cup calorimeter. Hopefully you remember to measure both the mass of the water in the coffee cup. Should be about 100 grams in around there. Good. And the temperature of the water before the block went in is probably going to be about 20-ish degrees Celsius. Good. Then you sealed up with this system and left it for a few moments so that the block of metal transferred heat to the water, and you came up with a final temperature for both the piece of metal and the water. It would be the same. Remember that when you calculate your temperature change, it's final minus initial, which means that your metal sample should have a negative value. Your water sample should have a positive value because it gained heat. Let's go back to the slide here. How was heat transferred to the metal block?
Conduction.
Pardon?
Conduction.
Within the metal block it would be conduction, but how did the heat get to the metal block? Convection. Okay. So this would have been on top of your heat plate here. So the source of heat was the heat plate. These particles would have become warmer first, and the warm water particles would rise and start colliding with the copper. Once the outer part of the metal became warm, then it could transfer heat to the center of the metal block by conduction. Absolutely. When you have conduction, it is only heat transfer through solids, versus convection is heat transfer through gases and liquid systems. In the second part of the experiment, when you put the block of metal into the coffee cup, how was heat transferred from the metal block to the water? Oh, but is the water made up of solids? No. So it was still transferred through convection because the warm particles touching the metal block would become warmer and then rise, and eventually cooler particles would fall next to the block and become warmer, distributing the heat throughout the water sample. There is some conductive heat transfer going on. Where?
Metal to the cup.
Okay, maybe the sides of the cup, or from the center of the block outwards. As the heat dissipated from the edges of the block, then heat would have transferred from the middle of the block to the outside of the block. You've probably tasted that with your food. So for example, you eat the edges and then it might be a little bit cooler, and then when you get to the center of your food item, maybe it's a little bit hotter because it takes a while for the energy to be dissipated from the center. When you consider the block that was added to the water, would you expect the Q value to be negative or to be positive? Oh, if heat is lost, you're going to have a negative Q. In the second part of the experiment, when you put the block into the water, which one was losing heat? The block. So the block would have the negative Q value. The water was gaining heat. So if I calculated how much heat the water was gaining, it would be a positive Q value. Number 4, a little bit more of a challenging question.
How could you do this one?
Once upon a time, people thought heat was a thing. It was stuff. And if I heated up something, I added stuff to that. So, what would have happened to the mass of the block if heat was actually made up of stuff?
It would have gained mass.
Yes, it would have.
So
But I'm pretty sure that when you felt that piece of metal on the end of the string, it was probably the same mass when it was hot that it was when it was cold. And that was the turning point. It seems so simple to us now. But remember, back in the 1700s, they didn't have the fancy scientific tools that you have even just in our science lab. So this actually shows how the caloric theory was disproved. It shows that heat is not a thing, because if it was a thing, the mass of the block should have become heavier, but it didn't. Today, we're going to do some practice calculations using a new formula. Q equals mc delta T. Then we'll apply the data that you collected in your lab in order to actually calculate the heat gained and lost by the substance. Put your lab in a safe spot because you're going to need that Monday. This is a data table. If you would like, you can put this data table with your periodic tables in that plastic sleeve, or if you're like other unnamed people, you can just randomly put it in your binder and hope you can find it later on.
I can find all of it.
All right. Q stands for quantity of heat. That's where the Q comes from. Finally found that 2 nights ago.
picture in the other sheet. I didn't get the other one.
Oh,
But I did get the
okay.
other responder.
Did you get this one? Heat's dependent on specific heat capacity. Can be determined using the following relationship. Heat is always dependent on how much stuff you have, how much you're changing the temperature of it, and how well it heats up or cools down, which we call the specific heat capacity. Unless we're calculating C, you're always going to have to look C up. On the front of this page, page number 4, you have quite a few elements from the periodic table. The most information we use is actually in the back. If you take a look on the back, you will often use one of the top 3 in this table: ice, water, steam. These are different phases of water. Ice is solid water, then we have liquid water, and steam is gaseous water. It is really, really important that when you choose the value to work within your calculation, you look at the question and see what is it actually asking me for. Because values are very dependent on their state. C values, for the most part in this class, we're going to be using joules per gram degrees Celsius because we generally use the mass grams in our lab. However, be aware that if we were working with industrial level applications, we would be using kilograms because we would be using much more, or much larger, quantities of substances. We're going to work through a couple of examples. It says on the first question, suppose on a summer's day, you notice that the concrete sidewalk you walked on previously is much hotter. If we assume that each block of the sidewalk has a mass of 5.002 times 10 exponent 3 grams, or 5.00 kilograms, a specific heat capacity of 0.840 joules per gram degrees Celsius, and we have an increase of temperature from 15 to 25 degrees Celsius, we should be able to calculate the amount of heat that was absorbed by the concrete in the sidewalk. This question has more information than what you're going to use. You are told 2 different masses. You're only going to be working with one of those masses. We're told a specific heat capacity, which is a C. This specific heat capacity is going to give us a clue about which of the 2 masses we should use. Any suggestions about whether or not you're going to use the grams or the kilograms? Why? Exactly. When you're choosing your mass, it needs to match what the mass is in your C value. If this was joules per kilogram degrees Celsius, then your mass should be in kilograms. Since this is in grams, we're going to choose 5.00 times 10 exponent 3 grams. The next piece of information is temperature change. Temperature change is always final temperature minus initial temperature. This is really important because substances heat up and cool down. Because of this, they're going to give us a negative Q or a positive Q. Is the concrete heating up by 10 degrees Celsius, or is it cooling down by 10 degrees Celsius? It's heating up. The way I know is the second measurement that's given is 25.0 degrees Celsius. The first measurement that's given is 15.0 degrees Celsius. That means that it has increased by 10.0 degrees Celsius. There's a lot of information to process with these particular questions. I like doing an information section or highlighting key things in my STEM question in order to help me identify what are the most important things that I'm going to use. What you do have to show is the formula you're going to use to solve the question. The question is asking you how much heat. That is Q. Therefore, your formula is Q equals mc delta T. The second step you must also show. The second step is that of substitution. That is when you put the numbers plus the units into where the letters are that represent those measurements. 5.00 times 10 exponent 3 grams times C, which is 0.840 grams, joules per gram degrees Celsius, times 10.0 degrees Celsius. Remember that when you put scientific notation into your calculator, to use the EE or the EXP button rather than going literally times 10. Otherwise, your calculator may do that, and you're going to be off by a factor of 10. EE or EXP takes the place of the times 10 part. Give it a try on your calculator. If you need to go get your calculator, go do that quickly, please. Give it a try on your calculator. You should get 4.20 times 10 exponent 4 as your calculated answer. You only get 3 sig figs here. What are your units going to be? How do you know, other than looking at the right-hand sideboard and seeing that's how you measure Q? Okay. So what I'm going to do is just rewrite the units over here so that we can see which ones will divide out. We have grams times joules over grams degrees Celsius times degrees Celsius. Sometimes when we put those units together like that, and get the numbers out of the way, it's a little bit easier to see what units will divide out. Grams divided by grams is 1. Degrees Celsius divided by degrees Celsius is 1. The final units for the question are in joules. Sometimes you're going to be asked to take one more step and represent that number in kilojoules. There are 1,000 joules in 1 kilojoule. If I have 4.20 times 10 exponent 4 joules, and I want to go into kilojoules, I need to come up with a conversion factor. This is the same style as what we did with mole ratios. This is the same style that you did with molar mass calculations in our last unit. It's what you need over what you have. You need to find kilojoules. You have joules in 1 repeating 0 kilojoules. There are 1,000.0 repeating joules. When you do your sig figs, look at your measurement rather than your conversion factor for this. Forty-two 4.20 times 10 exponent 4 times 1 divided by 1,000. Mm-hmm.
4.20 times 10.
Exponent, yeah, we can do times 10 or 10 exponent 1. Heat was absorbed by the concrete. As a verification, make sure you check your sign of Q. Sometimes it's not overly apparent that you're going to get a negative value for Q, and you have to add that negative value. So for example, if it says that the concrete lost 2,000 joules of energy, you would have to add a negative to 2,000 joules. Let's try question number 2. This is a really good example of where you're going to have to add a negative sign because it's not going to be immediately apparent as to where that negative comes from. Okay, in the evening, an iron statue in the park cools off from 25.0 degrees Celsius to 10 degrees Celsius. When it talks about 25.0 to 10 degrees Celsius, is that a Q, an M, a C, a delta T? It is a delta T. Delta T is final temperature minus initial temperature. The initial temperature of the statue was 25 degrees. The final temperature was 10 degrees. This is a really great example of how you come up with a negative value for a temperature change. The substance is cooling down. statue cools off, and in doing so, releases 336 kilojoules of energy. If it says loses or releases 336 kilojoules, is this a Q, an M, or a C? It's a Q. Since the question says that it releases heat, I must add a negative sign to this. The reason is heat is leaving the statue. Anytime we have heat being released, that's always going to be a negative Q. What is the mass of the statue? If the specific heat capacity of iron is 0.449 joules per gram degrees Celsius. Before we even start our formula work, there's one more thing that we have to do to this data. Two data don't match. Yes. If you look here, this is kilojoules. Here, that is joules. When I do my formula work, joules and kilojoules will not cancel out. Is it going to be easier to change kilojoules into joules? Or is it going to be easier to try to work with this one? It's going to be easier to work with this one because this one has 3 units in it. If I don't do my conversion correctly, that can have that can really make it challenging to try to sort out what to do with the other 2 units. Go with the easier one to convert. Okay, there's nothing wrong with doing that. Set up your conversion factor times. This time we need to find joules. Joules goes on the top. We have kilojoules, which will go on the bottom. There are 1,000 joules in 1 kilojoule. You can write that on your new data table. When you do your calculation, use the significant figures of your measurement because this is a unit conversion. It's exactly the same amount and an infinite amount of zeros. You could write negative 336,000 kilojoules. Or you can convert that into scientific notation and say negative 3.36 times 10 exponent 5. Once you start getting a lot of zeros in a calculation, it might be a little bit better if you convert it into scientific notation so that you don't forget zeros. Now we're ready to do something with a formula. Our base formula equals Q mcdeltaT. We're not looking for Q this time though. There's 2 ways you can tackle this problem. The first way is to rearrange your formula to solve for M. If I want to solve for M and isolate that, I need to divide both sides by C delta T. I can do it this way. I know that Q equals mc delta T. Q is negative 336,000 joules. I can make M my X. Then multiply by 0.449 joules per gram degree Celsius times the temperature change by negative 15.0 degrees Celsius. Then I can solve for X. Which one do you prefer to do? Rearranging the formula first? Or would you rather put in your values and then solve for the unknown?
Which do you prefer we do?
I'm not really worried about which way you do it. I would rather see that you do one way very well. Give it a try. Why did you multiply all three numbers together?
Or to try to find the match.
Multiply these two numbers together first. A lot of people are going to work with this method here. You can do this in a couple of ways. Some people prefer to multiply these two numbers together first. When you do that, if I multiply 0.449 times negative 15, I get the number negative 6.735. These are all the units that come together when I multiply this times this. Can you see something that's going to divide out in the units?
Celsius.
The Celsius. But I need to solve for X. How am I going to solve for X?
Negative 6.
Yes. And what I do to one side, I must do to the other side. Negative 6.735 divided by negative 6.735 is going to equal 1. What I do to one side, I must do to the other side. Joules divided by joules is going to be equal to 1. When you take negative 336,000 divided by negative 6.735, You should get 49,886 grams, but you're right. Awesome. Somebody's busting me on my sig figs. Good, you're awake this morning. I only get 3 significant figures.
4.98 times 4.
Oh, excellent. 4.99 times 10 exponent 4 grams is going to be the mass. That seems like a pretty high number. Think about when you measured your block yesterday. I think the maximum would have been about 80 grams. Oh, this is quite a bit higher. It should be because, what are you dealing with? Statue, right? A statue has far more mass. When you get to the end of your question, always ask yourself, does this number actually make sense? If you got an answer of 4.99 grams because you forgot to put the rest of your scientific notation in, that's about a tablespoon of sugar. That should be setting off some alarm bells, like, maybe this isn't quite correct. Example number 3 is going to have you solve for temperature change. I'm going to erase the board and get set up for the next question. Please go through and find the important information in that question.
Can you leave that?
All right, I'll leave it. Sure. I'll start doing the work on the board then. 100.0 grams of gold. Is that a Q, an M, a C, a delta T? Oh, so knowing your letters is half the battle. Okay, we're going to pause right now. Take out your brand new table. If you need a reminder about what heat is, what units are used, or what letter are used in the math formula, write that down. It's half the battle. If you can figure out which pieces of information correlate with which part of the mathematical formula, you'll be far further ahead. .0 grams is a mass. Okay. At 25 degrees Celsius. Aha. Okay, and that's really important. It's not a temperature change. It's the starting temperature. Very good. Quickly absorbs 140.8 joules of heat. Is that your Q or your C? Yes, Q. Notice that the word absorbs is italicized. It's trying to give you a hint. Yes. question is asking you to find the final temperature. This is after the necklace has been sitting on the person for a while and absorbed heat from their neck, and it's warmed up the gold particles. There's a couple ways that you can solve this. Suggestions? Okay. We can solve for TF because we know that temperature change is final minus initial. There's another way to do it. It's actually a two-part question in the second way. Is this board safe to erase now? Okay. If algebra with more than two operations really messes with you, you have a subtraction, a multiplication, and a division that's going to happen, you might prefer to tackle it this way. We know that the formula used is Q equals mc delta T. What some people prefer to do is first find delta T. Once they have delta T, then they go to the change in temperature calculation and find out the final temperature. Which way do you prefer? The other one? Okay. Let's fill in some information. We know that the Q is 154.8 joules. The mass of the necklace is 100 grams. The specific heat capacity of the gold, oh, I'm sorry, I did not write that down on the slide. Is 0.19 joules per gram degrees Celsius. We don't know what the change in temperature is going to be. We're going to call that X, or T if you want. It doesn't really matter what letter you give it. Multiply 100 and 0.129 together. Can you see a pair of units that will divide? Yes, the grams divided by grams is going to be equal to 1. You need to solve for X. How do we isolate X? We're going to divide by 12.9 so that we get x by itself. What we do to one side, we do to the other side. If you do that, you should get a temperature change of 12.0 degrees Celsius. That doesn't tell us the final temperature of the gold. It only tells us how much the necklace has warmed up by. We need to do this second step if we're going to solve it that way. The second step is temperature change is equal to final minus initial. You just calculated that the temperature change was 12.0 degrees Celsius. We don't know what the final temperature is. We know that the initial temperature was 25.0 degrees Celsius. We add 25.0, negative 25 plus positive 25 is going to be equal to 0. What we do to one side, we do to the other. Does a temperature of 37 degrees Celsius make sense? Do you think something sitting on top of you would get to a temperature of 37 degrees Celsius? Your inner core temperature is about 37.9 degrees Celsius. So it is possible for the gold to have this final temperature. There is one more variation of the formula. There's one more thing we haven't solved yet. The last example is going to have you solve for C. So this way, when you go to do your work tomorrow, you're going to have an example of how to solve anything in that Q equals mc delta T formula. I'm going to get this smart board ready. I think some people are still copying down the regular board.
Can I just do this instead of going to like this?
Okay. Alright, so then you would take 12.9 and you would multiply everything in the bracket by 12.9. So that would be 12.9 TF. And then
Oh
12.
no, that's not a bracket. That's a Celsius.
But this is within a bracket though. So I'll do it over here on the right hand side board. So alright, so we have 154.8 joules. Okay, so you're replacing delta T with TF minus TI.
Oh, okay.
Okay, so then 100.0 grams times 12, or 0.129 joules per gram degrees Celsius. TF minus 25.0 degrees Celsius.
Yeah. What? What? I heard my name though.
Okay, so then here, what I did was I multiplied these two together,
Yeah.
and I got 12.9. The next step is to multiply this by TF minus 25.0.
Okay. Then this.
I better get my calculator.